In Chapter 2 of this course, we look at the first type of cell model that we will look at in this course. There are two basic approaches to making mathematical descriptions of battery cells. The first approach that we look at here uses engineering principles and know-how and looks at how the output of the battery cell responds to certain input stimuli and tries to come up with what we'd call a black box kind of a model, or just generic equations of motion that describe how the battery cell works. The other type of cell model that we will look at in the following chapters really digs down inside the battery cell and tries to understand from first principles physics what are all of the different activities going on inside of the cell and making equations to describe all of those. We're starting with this kind, with what we call the equivalent circuit cell model, because especially if you have a background in electrical engineering, this is going to be a lot more comfortable for you as an introduction to cell models. And there are a lot of applications and uses for equivalent circuit cell models. For example, in the follow-on course, 5720, almost all of the work that we do in that course uses the equivalent circuit model, and perhaps at some point in the future we'll have a even follow-on course that does it with the physics-based models. So we're beginning our study of battery models by building up what I'm going to call a behavioral model, which tries to describe what the behavior of the cell is by looking only at the external signals, or a phenomenological model trying to talk about the macroscopic phenomena that are occurring and modeling each one of those phenomena separately and adding them together. And the model that we will build can be described using circuit elements from nonlinear and linear circuit theory. So the idea is I have an actual battery cell, here it is, but I'm going to say that that is equivalent in some way in its operation to a circuit that has a voltage source and maybe a resistor and a capacitor and a resistor, something like that, that these have some sense of equivalence, that they would operate the same way if I were to put them inside of an electrical circuit. And if you've taken a circuits course, you know what a voltage source is, you know what a resistor is, you know what a capacitor is, you know how they work together, and so the intuition you gain from this kind of a model will be helpful in interpreting the kinds of higher fidelity models that we look at in the following chapters. So these are helpful in getting a feel for how cells respond to different usage scenarios. And they're also adequate for some application designs also. But ultimately, we're going to need a deeper understanding, and that's why the course does not end after we finish Chapter 2. The approach that we take in this chapter is to develop a circuit model that tries to describe the battery cell as a plug-in replacement for a battery cell. Starting with the most important parts of what a battery cell does, and then looking at what our model does describe about the battery behavior, and then looking at what it does not describe. What it does not describe is the model error. And then we would propose different components to help reduce this modeling error until we get the modeling error down to a point where either we can't figure out anything better to do, or it's small enough that we don't care anymore. That's okay. So we start with the simplest possible model and add incremental complexity to that model to describe better and better and better how the battery cell works. So the ideal battery is modeled as an ideal voltage source, and here is a circuit diagram for an ideal voltage source. And so we have terminals. The positive and negative terminals are the positive and negative terminals of the battery, and there's a voltage across those terminals, that's V of t, and the battery cell may be supplying a current which is positive when it's supplying current to a load, and it's negative when it is being charged. And in this idealized model, we have a fixed voltage that we call OCV. And for different kinds of cells we're modeling, we would have a different value of voltage, but that's really the only parameter to our model is the value of this voltage source. So in this model, now please don't confuse the model with the reality because they can be quite different, but in the model, voltage is not a function of current, IFT. Voltage is not a function of past usage, current at previous points in time. Voltage in this model is constant, period, nothing else. Now, none of that is true of a real battery cell, but it does describe some of the most average behavior, perhaps, and so it might be a good starting point. We do know that batteries supply a voltage, and this voltage can supply power through current to a load. And when a cell is completely disconnected from a load, so it's unloaded, and it's in complete electrochemical equilibrium, we've let all of the chemical processes in the cell relax by resting the cell for a long period of time. This is a condition we call open circuit. When both of these are true, when it's unloaded and in equilibrium, the voltage is predictable. And so that's why this is called an open circuit voltage. And we will find that in our ultimate equivalent circuit model, we will retain a voltage source. Not exactly this, but we will retain a voltage source. This model doesn't describe a lot of things that happen in a battery cell, though. We need to have better fidelity. For example, we know that when a cell is fully charged and we measure its open circuit voltage, the measurement is going to be higher than if the cell was partially or fully discharged. So the real cell has a voltage dependency on how much charge it is holding. And this is a simple experiment to do. If you have any kind of battery powered device and a voltmeter, you can put the device on the charger until it's charged and then use your voltmeter to measure the voltage when the cell is fully rested. Leave it an hour or two and then measure the voltage. And then use the cell in its application for a period of time, and then again let it fully rest and measure the voltage, and you'll find that the voltage is lower. So we could improve our simplest model that we just talked about by including in some way some dependence of the output voltage of the cell on the charge status of this cell. And in order to do that mathematically in a model, we would first have to define what we mean by a charge status. And that is the point of this section right here. So we define a variable called the state of charge, or SOC, of a battery cell. And the symbol that we use in this course for state of charge is the letter Z, and it's a function of time. So Z of t is the state of charge of the cell at some point in time. And when the cell is at a level of full charge, we define Z to be 100%, or Z equals 1.0. And if the cell is fully discharged, then we define Z to be 0%, or Z equals 0.0. And at any point in between, Z would have some fractional value between 0 and 1. Now this is not an especially precise definition of state of charge. We can make it quite a bit more rigorous than this, but this definition will be enough for right now. Now, in conjunction with this idea of state of charge, we define a total capacity of this cell. And the letter that we use in this course to define capacity is Q. And Q is the total amount of charge removed when discharging a cell from its 100% state of charge to its 0% state of charge point. And Q is usually measured in ampere hours or milliampere hours. So, we can then model state of charge of a cell using quite a simple equation. And remember that the dot notation, as in z dot, means time derivative. So z dot is dz by dt. So z dot then is minus I of t over q. And so we see that state of charge will go down when current is positive. Remember, positive current is current leaving the cell, so charge leaving the cell. And z dot will be positive, or z will increase when current enters the cell. And then there is a scaling factor that's divided by q that will force z dot to go in the correct range from 0 to 100% as the cell is charged. If we are careful, and I'll say more about that in just a second, we can integrate this expression using Leibniz's rule for integrating a derivative and being quite careful. And we get then that this relationship that z of t, so state of charge at any point in time t, is equal to state of charge at some point in time t0 before t, so some point in the past, minus this 1 over q times integral from t0 to t of current over that time interval dt. A note on units. Z is unitless. State of charge has no units. It's just a number between 0 and 1, or 0% and 100% if you want to think about it that way. I of t has units of amperes. And when I integrate with respect to time, the result of this integral has units of ampere seconds. And so for us to come up with a unitless quantity, Q here must have units also in ampere seconds. And notice 1 ampere second equals 1 coulomb. And since Q is usually measured in ampere hours and milliampere hours, I usually have to then write this instead as 1 over Q times 3600 to convert from amp hours into ampere seconds or coulombs. But in any case, I've got a state of charge equation, and this is given a name, by the way, that I may use from time to time. This is called Coulomb counting. Coulomb counting. 1 ampere second is 1 coulomb, so we are counting the number of coulombs that go into the cell or out of the cell by this running integral, and we're subtracting that, properly normalized, from the state of charge in order to say how those coulombs entering and leaving this cell are impacting the state of charge. And this is one approach to estimating state of charge. It turns out to be a pretty bad approach to estimating state of charge, but it's at least a first approach that we look at when we examine that idea in 5720. In discrete time, as most of our models are going to be formulated ultimately in this course, if we assume that the battery cell current is constant over some short sampling interval delta t, then we can write that the state of charge at time sample k plus 1 is equal to the state of charge at time sample k minus I of t times delta t over q. In other words, we replace this integral over a period delta t by I times delta t using a rectangular integration approach. That's a pretty good equation for state of charge. There are some things we could do to make it a tiny bit better, though. One is to recognize that the battery cells are not perfectly efficient in the sense that when I charge a battery cell, I might push, say, 1 ampere hour of charge into this cell, but later when I try to discharge the battery cell, I am not able to retrieve that entire 1 ampere hour of current back. There's an inefficiency, and the reasons for this inefficiency have to do with certain side reactions, chemical side reactions that occur inside of this cell that are usually not desirable Sometimes they lead to aging and sometimes they don't. But if you imagine I've got an input terminal to this cell and an output terminal and pushing current in, that most of the current goes into some reaction that charges the cell, but there's a little bit of current that takes a side path that does not charge the cell. It does not change the composition of the chemical formula of the cell such that I can extract that charge back. And we can take that into account in our equation by introducing an efficiency factor, eta. This is not an n, it's the Greek letter eta. And so going back to the continuous time definition, we would say z dot of t equals minus I of t times eta of t over q, or in discrete time, it's minus I of k, eta of k, delta t over q. This term, this efficiency term, is called the coulombic efficiency of the cell. It has to do with how many coulombs we get out for every coulomb I put into the cell. And we model this efficiency as less than or equal to 1 on charge, close to 1, usually around 99% for a lithium-ion cell. Because we're losing some of this charge to a side reaction. And we usually model the efficiency as exactly equal to 1 on discharge, partially because these chemical reactions are not usually excited on discharge and partially just due to ignorance, that we don't know how much of the efficiency is lost due to charging and how much is due to discharging. And so we will set one of them, the discharge one, to perfect and then blame the charging for all of the inefficiency. But in reality, almost all of the efficiency lost are on charging and not on discharging. We also need to be careful. There are at least 2 different ways that we talk about the efficiency of a lithium-ion cell. One of them is coulombic or charge efficiency. The other one is energy efficiency. Coulombic efficiency is what we're talking about here. Coulombic efficiency is around 99%, and it's equal to how many coulombs of charge I can get out for every coulomb of charge I put in. Energy efficiency is different. Even if coulombic efficiency is perfect, I might have some energy inefficiency, and it's usually more closer to 95% or something like that for a lithium-ion cell. And energy efficiency is equal to energy out divided by energy in. And the way to have imperfect energy efficiency is to have power loss. And one way to have power loss is if I have an I squared R kind of power due to some resistance in this cell, and the current going through that resistance heats up that resistance, and that's a power loss right there. So I'm losing power but not charge in the process of doing that. We'll look at a resistive model in a few sections, but for now, just understand that energy efficiency and coulombic efficiency are different things, and right here, eta is the coulombic efficiency. So we have an expression now that describes the dynamics of state of charge. It's an ordinary differential equation in continuous time or an ordinary difference equation in discrete time that states this is how state of charge will change as I add current or subtract current from the cell. And since we said that it was our observation that a battery cell had typically higher voltage at higher states of charge and lower voltage at lower states of charge, we can think of plotting the open circuit voltage as a function of state of charge for whatever battery cell we are trying to model. In this figure here, I show 3 different curves for experimental lab test results plotting open circuit voltage versus state of charge for 3 different lithium-ion cells. So state of charge down here, it's in percent. Open circuit voltage is in volts, and we go from 2.5 to 4.25 volts in this figure. So notice all 3 of these are some kind of lithium-ion cell or another, but they have different characteristics and quite different. This one here is a cell that has a lithium iron phosphate positive electrode. This one here, if memory serves, is lithium manganese oxide positive electrode. And this one here is some kind of a blended material positive electrode that has some lithium manganese oxide, maybe some lithium cobalt oxide, and maybe even some NMC in it as well. The manufacturer doesn't usually disclose all of this information to you, exactly what the chemical compounds are. Some of them are pretty easy to tell. This 3.3 volts is very characteristic of an iron phosphate cell. And the other ones, there are some other telltale signs that we could guess, but they don't always tell you. A little later on in this chapter, toward the end, I'll describe how we can perform lab tests to find this open circuit voltage relationship, but for now let's just say that it's possible to do this. And let's also state, without any kind of proof, that open circuit voltage is a function of state of charge, and that's the dominant effect, but it's also slightly a function of temperature. And so we could say that open circuit voltage is represented like this. It's a function of state of charge, Z of t, and it's a function of temperature, capital T of t. The temperature change is relatively small. It's usually less than a millivolt per degree Celsius, and so even over a range of 100 degrees Celsius, which would be a huge operating range for one of these cells, we're talking about less than a tenth of a volt of absolute difference. So it's not a huge impact, but it can be an important and noticeable impact in the voltage curve. We have defined state of charge. While we're still talking about that, I'd like to define something called depth of discharge, or DOD. That's pretty commonly seen. It's the inverse of state of charge, the additive inverse. So depth of discharge is 1 minus state of charge if we're talking about depth of discharge as a fraction. So if SOC is 100%, then DOD is 0%. There's no discharge. If state of charge is 0%, then depth of discharge is 100%. I'm fully discharged. Sometimes you'll also see depth of discharge with units of ampere hours or milliampere hours. And if you see that, what they are doing is they are multiplying the fraction by the capacity of this cell. So they're saying, instead of fractionally how much is this cell discharged, it's in total amount of ampere hours. How much has this cell been discharged? And because of this simple relationship between SOC and DOD, I could just as easily plot the voltage curve versus DOD, and it would just flip it around. And so I would have a plot that would look something like this instead, with DOD on this axis and OCV on this axis. You'll see both types of plots in practice. So that concludes our look at our first couple of models, and in the next section we will continue to develop even more fidelity in this model.